Are you guys just waiting on one more? Yeah. Okay. Okay. Yeah. If he shows up, we can pause and y'all can get your thing out of the way. So just let me know. Or obviously I can see. So I will keep my eyes on him. All right. So in the meantime, hydrogen. All right. So hydrogen is a kind of interesting topic with sustainable energy because it's has a lot of uses, and it's still kind of up in the air exactly what the best use of it is going to be in the energy transition, going to a completely decarbonized energy supply. But it's definitely something that I think we're going to be seeing more, using more of in the future. So it's good to think about. Okay, so we're going to start out with talking about how we actually make hydrogen. And the reason for this is that there is naturally occurring hydrogen. Many of you have probably heard about this geologic hydrogen stuff. It's not entirely clear right now what the total resource potential of geologic hydrogen is. So right now, all the hydrogen that's used around the world is made, it's manufactured. So it's a good deal to understand how that hydrogen is made. Should we pause? You guys want to come get set up? All right, fantastic. All right, we're going to pause for a group presentation. Okay, back to hydrogen. So, the question is, why would we even consider using hydrogen in the first place as an energy source? Well, here's the main motivation behind this is that we already have a lot of infrastructure that is designed to burn something as a fuel source, and we also have a lot of pipelines. And the idea of moving a fluid around is fairly well established in the our energy supply. And so the question is, can you burn a fluid that doesn't emit carbon dioxide? And hydrogen actually fits that bill pretty well. And it actually ends up having a bunch of other uses as well beyond just burning it. In fact, burning it might even not be the best use scenario. So we'll see about how some of that might work. But here's the general idea. So when you burn hydrogen, you're combining it with oxygen and you produce water. So that's the byproduct of combusting hydrogen. It burns hotter than natural gas. So you can see it's about 200 and almost 300 degrees hotter than natural gas flame. And it combusts so hot in pure oxygen that it's got a major use as a rocket fuel right now, and has been since the early days of space exploration. So you can burn it, but the other thing you can do with it is you can form hydrogen by splitting apart water into hydrogen and oxygen. And if you run that process in reverse in something called a hydrogen fuel cell, you can actually generate electricity. And we'll see how that works in a little bit. But basically, the hydrogen goes in. The protons, move across this electrolyte here. They generate an electric current, and then you combine it with oxygen, and it makes water. So that's another big use of hydrogen that we might be seeing in the future. And this is just a little bit of interesting trivia, but the first internal combustion engine was actually designed to use hydrogen. It was called the de Rivaz engine in 1807. And the way it worked basically was that the hydrogen was kept in this balloon here, and it was kind of a crank operated type system. So you've got the hydrogen in here. There's a spark igniter here, and so there's a combustion chamber. And so it works, kind of the same way a regular, internal combustion engine works. The spark moves this piston up, which drives this ratchet, which then pulls the pulls the whole thing forward. And so it's hand operated though, in that you have to use this crank here to pump the hydrogen into the combustion chamber. So it's still a little bit using, human energy, but it's kind of an interesting idea. So anyway, so going back to the 1970s, there's been, ebb and flow in interest in the use of hydrogen. Starting in the 1970s with the oil price shocks that occurred back then, the International Energy Agency formed a program looking at use of hydrogen as an alternative to fossil fuels. So that was in 1977. In the 1990s, we started getting a little more awareness about climate change and thinking about what might be used as alternative transportation fuels. And there was this law that was passed in 1992 here in the US called the Energy Policy Act. And it codified a bunch of acceptable alternative fuels, including liquefied petroleum gas, liquefied natural gas, but also hydrogen. In the early 2000s, there was more climate change concern, but also this was pre-fracking revolution. People were honestly concerned that we were going to run out of oil, that we had reached the peak production and the production was going to irreversibly decline after that. And so we would need something else as a fuel source. And so you saw these, international partnerships formed to, increase, our awareness and develop new sources of energy, including hydrogen. And that, interest kind of then cratered in the late 2000s when we figured out how to produce oil and natural gas from shales. And so that removed that peak oil concern. And now in the 2020s, hydrogen is getting attention again because of people's awareness about its use in the energy transition. So we're right now kind of at the crest of a wave of interest in hydrogen, and who knows, maybe we'll decide we don't need it. But at least for right now, it's still a big thing that's out there. Now, right now, most of hydrogen is used either as a feedstock in chemical refining plants or as a feedstock in ammonia plants. Okay, and then there's a few other kind of smaller uses. And so you can see that hydrogen use has grown considerably from the 1970s. This is in millions of metric tons of hydrogen per year. But so in 2018, we were using about 70 million tons per year. And again, it's mostly in these industries that, either for fertilizer or in chemical plants for various processes there. But there's a lot of potential uses that we could be seeing. This is a bar diagram of, this is as of 2018. I think the IEA has published a new hydrogen update, but I think I looked at it and didn't really have anything beyond this. Anyway, but as of 2018, this is a graph of the number of countries that have various policy incentives in place for other uses of hydrogen. You can see, passenger cars, vehicle refueling stations, so a lot of interest in its use as a transportation fuel. But also, heat and power, electricity, and then other industrial uses. So there's a lot of potential for the use of hydrogen in the future. And you find a lot of cool graphics online about hydrogen, but this is maybe my favorite. It's called the Clean Hydrogen Swiss Army Knife. And it illustrates all the different things that hydrogen could be used for in various sectors. So there's a lot, right? So electricity generation, chemicals, aviation, transportation. So, you think about it, it could, be a significant part of our future energy system. But the word could in that sentence is doing a lot of work because The availability and manufacture of hydrogen right now is just not there to meet what the future demand would be if we're using it for all this stuff. So there's a big challenge in scale. Okay, here's another cool graphic, the hydrogen ladder. Now, this one grades hydrogen end uses in terms of, basically how good an idea they are, whether they would be competitive with other technologies. And it's color-coded here by, different end uses. So we've got electricity generation. We've got, could be replaced or it could be substituted for biogas or biomass. And then the maroon here, those are uses where there's really no alternative. And so these things include fertilizer, which we talked about, that's ammonia plants, hydrocracking and desulfurization, which are processes that happen in chemical refineries. You need hydrogen for that. Excuse me. And hydrogenation, that's another chemical process. And then methanol manufacture, you could be using hydrogen for that as well. But then some of these other ones, so for instance, domestic heating, automobile fuel, it turns out that maybe hydrogen is not the best thing for those. There could be other sources of energy that we could use that actually would probably be cheaper and more efficient. So it's really important to remember that. You can't just say, oh yeah, let's use hydrogen for that. There's a lot of considerations that need to go into that. Okay, so the engineering challenge with hydrogen is summarized in this slide. So there's a lot going on here, but right now, given that geologic hydrogen is not really a thing yet, we're not producing, very much in the way of geologic hydrogen at the moment. The predominant source of hydrogen is being made in a chemical plant. And so you've got this whole, what we call the value chain, which is, the supply end, the handling end, and then the demand end. And there's all these different flows of hydrogen among these different systems. Basically you've got to make it, you've got to store it somewhere while it's not being used. You have to transport it to the place of end use, which we'll see is a challenge in itself. And then there's all these potential downstream demands right now that you could see. So it's a big, complicated system. And we'll kind of break this down over the next few days and look at what the specific challenges embedded in it are. Okay. When you think about the actual form that the hydrogen is in, some of these end uses can use just pure gaseous hydrogen. So the ones that I've highlighted in bold over here can, basically just take the hydrogen gas and use it straight away. And that's basically everything except aviation fuel. Right? You're not flying around airplanes with hydrogen on them because of basically the Hindenburg. Right? So I shouldn't laugh about that. But we all know what can happen. But another potential form of hydrogen is actually as ammonia. We'll see that ammonia has actually a lot of useful properties. You can burn it itself as a fuel. It's easy to transport because it can be liquefied easily. And so a lot of these end uses over here can also use ammonia, including shipping and trucking fuel, electricity generation, and also in the chemical industry. So, you're starting to see that you can have hydrogen in different forms for different end uses, and there's a lot of possibilities here for how you can go about using it. Okay, so let's talk real quick about how we make hydrogen. So there's really 4 different processes that you can use. The first 3 up here, which start with natural gas, oil, coal, or biomass, they're all more or less the same, where you gasify the hydrocarbons that are present in those materials, and then you run them through a series of chemical reactions that produce hydrogen. Okay. As we'll see, a lot of the current day processes using these, starting feedstocks emit a lot of carbon dioxide. So if you're going to scale up production of hydrogen using these feedstocks, you're going to need to abate those carbon emissions somehow. Down here, this process is called electrolysis, and this is where you start with water, you split it apart, and you make oxygen and hydrogen. And so that, depending on where you're getting your electricity from, there can be less carbon emitted, less CO2 emitted from this process. In a perfect world, you would have completely renewable generation powering electrolyzers that are making your hydrogen, so there's no carbon footprint at all, but we're not there yet. Okay. And then, once you make your hydrogen, there's a bunch of other stuff you can do with it, which, the big ones over here are going through the Haber-Bosch process to make ammonia, and we do a lot of that today. And then the other one is these processes that happen in chemical plants that are used to make synthetic hydrocarbons. There's actually a really cool idea that's out there right now, and I'm not really sure if it's ever going to be fully realized, but there's these things they call them e-fuels, and they are made by synthesizing carbon dioxide together with hydrogen to make synthetic hydrocarbons. And it is possible to do that in such a way that you have net zero carbon emissions if you remove CO2 from the atmosphere with direct air capture, use that to make your e-fuels, you burn them, you release the CO2, but then you recapture that CO2. So even though you're emitting carbon dioxide by burning the hydrocarbons, you're abating that CO2 by using captured CO2 from the air. So it's kind of an interesting idea. Question over here.
That cycle?
No, because the direct air capture takes energy. And so you have to think about where that energy is coming from. Also, I'm not really an expert on chemical plants, but these processes do require energy inputs as well. So as long as that energy is coming from a net zero carbon or no carbon source, then, so there's a lot of ifs in there, but you could, theoretically, you could make it work. So we'll see. I know there's a lot of people working on that right now. Okay, so today, standing here, 2024, 76% of the hydrogen that is consumed comes from either natural gas or oil. 23% of it comes from coal gasification, and less than 2% comes from electricity. So we may see that mix change in the future, but that's where it is right now. Okay, so let's talk a bit about these processes. So kind of the simplest one to understand is making hydrogen from natural gas. And this is usually done in a process called steam methane reformation. The way it works is that you have an incoming stream of natural gas, which is mostly methane, and you use some of that methane to heat the furnace here up to 700 to 1,000 degrees Celsius. And then the remaining methane goes into the furnace where it reacts with steam and generates carbon monoxide plus hydrogen, okay? Now, what comes out from this process is CO2. So that comes out of the flue gas. Then you take the carbon monoxide and hydrogen. That mixture is called syngas. It's useful for a lot of different things. But in this case, it goes through a cooler, and it goes through this reaction called the water gas shift. And what that does is it oxidizes the carbon monoxide to CO2, and it retains the hydrogen. And then you go through a pressure swing adsorption separator that allows you to extract the hydrogen and then remove the CO2. So you've got two streams of CO2 coming out of here, and then you've got your stream of hydrogen coming out the other side, okay? So this outgoing CO2 is a big problem, obviously. I think we'll talk about that more in a minute. Okay, so the actual reactions that go in here, and the steam reformer, it produces carbon monoxide and hydrogen. And so it is endothermic, and that's why you need to heat it up very hot. It also takes a catalyst. Okay, so now we're talking about critical minerals, And most steam methane reformers right now use a nickel-based catalyst for this process. When you go to the water-gas shift, this is an exothermic reaction, which is why it takes place in a cooler. And it also needs to be catalyzed. Usually you're using an iron-chrome catalyst or a copper-zinc oxide catalyst, okay? So again, critical minerals, copper is expensive, so there's a few other challenges baked into this. And then sometimes you'll see this process called autothermal reforming used, which is a little bit different than the steam reforming and water gas shift, but the result is the same, okay? So the big issue with steam reformers is how much CO2 is produced. So right now, so we saw that it was 76% of hydrogen supplies made by steam reforming either of natural gas or oil. And it is done completely without carbon capture. So actually, the hydrogen industry right now is a big emitter of carbon dioxide. ExxonMobil right now is starting a pilot project at their Baytown refinery where they're going to be trying to capture the CO2 from they have a hydrogen plant there. So they're going to be capturing the CO2 from that. And I think the plan is to sequester it actually offshore, which is kind of an interesting idea. They got some lease blocks fairly close to shore, offshore Galveston, and some old depleted Miocene sands that were produced back in the, I think, 1970s. And I think the idea is that they're going to pump the CO2 into those formations. So we'll see if that works. It's an interesting idea. It'd be really cool if it did, but there's a lot of challenges obviously associated with that. And with current CCUS technology, you can capture about 90% of the CO2 that's emitted. So obviously we would like that number to be 100%. So there's another technology challenge right there. Okay. Now, one thing I want to point out is the cost of including CCUS on the production of hydrogen. So right now in the United States, hydrogen made by steam methane reforming costs about $1 per kilogram. And the US Department of Energy launched this initiative a couple of years ago called the Hydrogen Shot. And one of the goals of the Hydrogen Shot initiative is to reduce the cost of low carbon hydrogen to $1 per kilogram, essentially to make it cost competitive with current technology for generating hydrogen. Now you can see that that's a bit of a challenge. So right now, if I'm running a steam methane reformer in the United States and I want to include CCUS, that bumps up the cost from $1 per kilogram to $1.50 per kilogram, which doesn't sound like a whole lot. It's only 50 cents, but that's a 50% increase in the overall cost. And so you're going to need to bring that cost back down. The other thing that's kind of baked into these prices is the actual price of natural gas. So natural gas in the US right now is absolutely dirt cheap, okay? So it's, could be an attractive source of hydrogen, and we are probably going to have an easier time here bringing that price down. But if you look at places like Europe or China, which has much more expensive natural gas, it's already expensive to make hydrogen. And if you add CCUS, it gets even more expensive. So, worst case scenario in China, if you incorporate CCUS into your steam methane reformer, you're up to about $2.50 per kilogram. So there's a lot of challenges here that aren't necessarily technological because they also get into the dynamics of the natural gas market. So that's another thing you have to think about here is the cost of your feedstock. Question over here.
Their goal of they want to make it the same prices without CCUS, that's the goal, that IEA thing. But how could you're adding something? If it's inherently more, and you're doing more than the original one, how would that
Yeah, so that's a good question. How could you even ever make this column the same height as that column? Because and the answer to that is that you need to make the operating expenses and the capex the same or smaller than the case of a normal steam reformer. So how do you do that? Well, you need to design the system in such a way that it costs less to build and operate. And so that's where the challenge is right now. It's not, we know how the process works, and maybe you can make the process more efficient too. Because if I go back here, okay, so I'm burning some of my methane to heat my furnace. What if I use something else that was cheaper to heat my furnace, like an electric boiler driven by nuclear energy or something like that, right? So there's opportunities in here to redesign the whole system. And so it's not just let's add CCUS and make it cheap, but it's let's integrate CCUS and make the whole thing more efficient that they're going for. Yeah. Okay. The other main method that you can use to make hydrogen is electrolysis. And the way this works is water comes in and you run an electric current across this electrolyzer. And that causes, if you've got electrons moving from left to right, that's going to cause the hydrogen H plus ions to break off the water and move from right to left so that you've got electroneutrality. And as they do that, they pass from the anode to the cathode and onto a catalyst, which combines the H pluses together to make H2. And so, right, because they have to be combined with some electrons. And so that H2 stream comes out, and then the O2 stream comes out on the other side here. So you split apart the water, okay? An electrolyzer, you need at least 1.23 volts of potential across it. And the electrodes are often nickel, platinum, or iridium. So here we are back to critical minerals. That's how the whole thing works. So it's a pretty straightforward system, except for the elements that you need in the electrodes. There's several technologies that are already pretty mature. Alkaline electrolyzers are the most common, and they use nickel-based electrodes. You can also use a membrane called a proton exchange membrane, which requires pure water, which is a major drawback of electrolysis, and they use platinum and iridium. And then there's some more interesting electrolyzer technologies that are actually being worked on as we speak. So the downsides here is that you do need electricity. And like I said, if you're using an electricity source that has a lot of CO2 associated with it, you're not really coming out ahead. Also, this is a really great quote. If we took all of today's hydrogen output, this is from 2019, which was 69 metric tons, if you made that completely using electrolyzers with current technology, you would need more than the total electricity generation of the European Union. So that's a lot of electricity that you're going to use to make a lot of hydrogen. So you need to think carefully about where that electricity is coming from. Are you competing with other end uses of that electricity? So there's a lot going in there. It also requires water. Right now, electrolyzers need that water to be pure. So you need to spend energy and money purifying it. It actually uses more water than steam methane reformer, which is kind of interesting. They're working on electrolyzers right now that I think can run using seawater, so that's kind of a promising step. But right now, that's not a very mature technology. Also, if you're using water, you're competing with other end uses of that water. For instance, to grow food, which food is good too. So there's a lot of trade-offs associated with electrolyzers, at least in their current form. So they don't emit as much CO2, but there's a lot of buts. Okay. I'm going to stop there for today, and I hope you all have a fantastic weekend. I'll see you Monday.